All right. Key topics to remember from all the stuff that we've learned so far. First unit, we talked about limits. And when it really got important when we talked about limits at infinity, we also have to remember limits at certain values. So, answer the first one. Limit as x approaches negative infinity of 3x squared plus 4 over 2x minus 3 is what? Good. The numerator is growing faster than the denominator. The entire thing will get larger. Well, it's just bigger. Yeah. So you'd also definitely pay careful attention to the sign. The numerator is going to be positive, but the denominator is going to be a negative. So positive divided by a negative gives you that negative. Second one, what is this? 0. The denominator grows faster than the numerator. So as the denominator gets bigger, the fraction is going to get smaller as a whole, and eventually it'll approach 0. And then the third one is what? Yes, if the degree is the same, we use the coefficients. Also making sure we're careful about the sign. But it usually just works out nicely. It might always work out nicely, actually. Now let's look at this. We didn't really look at this much when we did limits at infinity, but it's important. What is this limit as x approaches infinity? Good. We plug in bigger values for x, this is going to grow. E to a bigger value will just continue to produce bigger and bigger values. Okay, of course, if you have a limit that's equal to infinity, you can say it doesn't exist. So this equals negative infinity or does not exist. This equals infinity or does not exist. Okay? Because the definition of a limit is that we have to approach some value c, and if we're approaching infinity, we're not approaching a value, a specific value. It just keeps getting bigger or smaller. What about the last one? Excellent. A lot of people forget about this. If we have e to the negative infinity, well, I can rewrite that as 1 over e to the infinity. This will continue to grow. 1 over this huge number will approach 0. Very, very important to know the distinguished, how to distinguish between the two. Okay? Sweet. What if we're approaching a value, like the limit of this function as x approaches 2? First thing we want to do is see, is the function defined at 2? Because typically, like, we don't have asymptotes or holes or stuff, and we can just find the limit by finding the function value. Well, I plug in 2, and I get 0 over 0, which is indeterminate. Doesn't mean that the limit doesn't exist. It just means my function value doesn't exist at 2. But maybe we have a hole at 2. And maybe we have a situation where we can find the limit because we're going to be approaching this hole, but we can't find the function value. We could, if we had our calculator, plug in values like 1.99999 and 2.000001. And our calculator would be able to give us the value that we're approaching. But typically you won't be given a calculator when asked to do this problem. Instead, we would factor. And we would try to simplify our function and remove our hole so that we'll have some new function that will essentially mimic this, but will fill in this dot that we're missing. And this new function will be able to evaluate it too. I can find the limit as x approaches 2 of x plus 2. That's just 4. Well, that's going to be the same as this limit. It's going to be 4. And this is the situation. This is the graph of x plus 2. This is also what the graph of x squared minus 4 over x minus 2 looks like, except x plus 2 fills in the hole that this function has. Now, before we get into this, let's remember what this is. Does anybody remember seeing this? Exactly. The derivative formula. It's the first thing we used to find derivative functions or derivatives of something at a point. Okay? This is the definition of a derivative. What is that formula essentially? Slope. Exactly. Slope between 2 points that are getting so close to each other that they're practically on top of each other. H would be the distance between the x distance between the points. This would be the change in the y's between the 2 points. Change in y over x as this distance approaches 0. That's the definition of a derivative. That's how we find the slope of a tangent at a point. Okay? We forgot about this because we learned rules for derivatives. But when we first started out, I'd give you a problem like this. What is this? And don't write this down, at least all my work. Okay? What you guys would do you would distribute this stuff H. Okay? And then you'd cancel this and this because x squared minus x squared goes away. And then you would get rid of an h everywhere, right? And you'd have a limit as h approaches 0 of 2x plus h. Well, then you'd plug in 0 for h and you get 2x, right? Well, you're going to be able to do that without all the stuff in between. You'll be able to, I'm going to move this 2x right here. Do this now that you know the connection. Why? Yeah, the derivative of x squared is 2x. You guys know that. So, what if I gave you a problem like this? You're not going to do this by hand. Take you forever. But you're going to give me the answer. What's the answer? Yeah, it's just 5x to the fourth. The question, this limit as h approaches 0 of this, is essentially what is the derivative of x to the fifth? Well, I shouldn't have erased it. The definition of the derivative is x or f of x plus h minus f of x over h. Well, f of x, that's the function that we're taking the derivative of. Okay? Let me write that out so that it's a little bit better. Okay? So, what if I said, what is this? What's that? Just the derivative of log x. This is the same thing as asking you, what is the derivative of log x? You know the derivative of log x is 1 over x. Well, let me give you one more, and this is a challenging one. What is this limit? So plus h. What is that? Don't shout it out if you get the answer, but figure it out. Wow, look at that. Okay, I'm just going to leave it up like that. I don't see many pencils on paper here. You got it? What is this question essentially asking? What is the derivative of not negative, but of just cos of pi over 4? Good. No. 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 Nope, 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 nope. It's 0. Why? The cosine of pi over 4 is a number. Cosine of pi over 4 is root 2 over 2. What's the derivative of root 2 over 2? 0. There's no negative signs. There's nothing like that involved. It's just what's the derivative of a constant. Yeah, it's tricky? Yes. Along with Unit 1 and 2, we talked about continuity, and we might as well talk about differentiability at the same time. Function is continuous if at every function value the limit is the same at that value. Or you can just think, I don't have any holes, I don't have any vertical asymptotes. I don't have that, I'm continuous everywhere. Continuous is spelled wrong. Differentiability, you have to be continuous to be differentiable. That's the first thing. If you are not continuous, you're not differentiable. But you also can't have any cusps or sharp points. Okay? Because if we have that, then the limits of the derivative will not approach the same value. So the reason why we could take the derivative here is because the derivatives, as we approach this value, will approach 0, and here the derivatives will approach 0 as well from the right, whereas at a cusp, our derivatives will approach positive infinity as we get closer here, and they'd be approaching negative infinity from the right side. For like sharp points, we'd have a negative slope, positive slope. They're not approaching the same value, so the derivative does not exist at those points. Okay? If you are told that you are differentiable, you can assume safely and correctly that your function is continuous. If a question says that f is differentiable, you are assuming it's continuous. If you're told your function is continuous, you cannot assume it's differentiable. It does not work that way. You can have a continuous function that has a sharp point or a cusp or something like that. And you are not differentiable at those points. Okay? Let's just remember what a derivative is. What is a derivative? Instantaneous slope of a curve at a point. That's a derivative. Slope. We could have derivative functions. We could have derivative values. Derivative rules we learned. Just don't forget the product and the chain rule. If you need to practice that, do so. You may have to factor to find the correct answer, like number 2 on the practice test you took. You need to know how to take your calculator and find a derivative at a point. Let's make sure we can do that. So practice this using your calculator. Find the derivative of x cubed as x approaches 3 using your calculator. Make sure you get 27 in your calculator. We'll practice that when we go over some problems. Also, remember the derivative of position is velocity. The derivative of velocity is acceleration. The derivative of position is velocity. The derivative of velocity is acceleration. Okay, 2 ways to plug it into your calculator. You'll either have the n derived pop up so that it looks correct in your calculator, or your calculator will show up as n derived. The derivative of x cubed as x approaches 3. Okay, so math 8 is n derived. You can either pop up like this or this. Take the derivative with respect to x of x cubed as x approaches 3. We plug the value that we're evaluating at there. We plug in our function in the parentheses. If it doesn't pop up like this, and it's, I feel like I can change this. Yeah, in classic mode. You would go math 8. You'd say, take the derivative of x cubed, comma, with respect to x, comma, when x equals 3. Okay? There's a second way. It's actually maybe easier for you to understand and remember. You can graph x cubed. Okay? And in the calculate menu, you see dy dx. And you can tell your calculator to evaluate it wherever. So the derivative at 2 of x cubed is 12. Okay? Didn't focus on that much in this class because they're easy problems once you understand how to do them. Reyes? She was last class. She's not here right now. Like, I'll see them Wednesday. Who's this? She's eventually in my class as well. No, I'll lose them. Okay. Sorry. They just got the wrong class number. Okay. Special derivatives, implicit derivation, and related rates. We should know those special derivatives. I can change this 2.3 with any number. It's just the number to the x log the number. Really can be applied, this rule, with e to the x. Log of e is 1. So we don't do that. You can say this is e to the x log e, which is just 1, which is just e to the x. When we're implicitly deriving things and we encounter xy's, do not forget to use the product rule, f prime g plus g prime f. And when you're asked to find a rate of change with respect to time, you should be thinking d dt. Take the derivative with respect to time. Whenever you see things that are like units per second or units per minute or anything per time, you're thinking of related rates and deriving with respect to time. Instantaneous changes of things with respect to time. Well, they all are. So it makes it a related rate. It has a change in quantity with respect to time. Okay? Curve sketching. Be careful reading problems. Make sure you know what you're given. If you're given the graph of f prime and you're asked to find, where f has a maximum, you're not going to say the maximum's up here if this is f prime. You'd say the maximum would be here because we know that maximums occur when f prime goes from positive to negative. Also, the sign of f double prime would be concavity. We have an inflection point where the sign of f double prime changes, okay, from positive to negative or negative to positive. We have maximum, we have relative extrema when the sign of f prime changes from positive to negative or negative to positive. Remember that we could have extrema when f prime equals 0 or when it's undefined. Don't just set the derivative equal to 0. Also see if the derivative is undefined anywhere, because at those points you might have extrema. Okay. Let's look at a problem in your practice exam. This was the worst performing problem from the exam. It was problem number 19, I think. $14. 14 was the worst performing problem out of the entire practice test. We're given the graph of position, x of t. Shown above, time is between 0 and 6. So the graph has horizontal tangents at 1 and 5, and the point of inflection is at 2. Ask what are the values of t? For what values of t is the velocity of the particle increasing? Okay. 1 out of 10 if you got this right. Let's break this down. If I ask you, when is f increasing? How would you answer that? Look at f prime, right? And you'd see when f prime is what? Positive. Okay? When f prime is positive, that will tell me when f is increasing. Well, what if I asked you, when is f prime increasing, what would you do? What's up? Yeah, you would eventually look at concavity, but you're just seeing when is the derivative of f prime positive, right? So if you're looking at whether something's increasing or decreasing, you take the derivative and you see when it's positive or negative. Well, this question is, for what values of t is the velocity increasing? So the question is, when is v of t increasing? What would we have to look at? Yes, we'd have to look at when v prime is positive. V prime is the same as A. Or if you think of this as being f prime, this is f double prime, and f double prime is positive when f is what? Concave up. So, what's the correct answer for 14? A. Everybody assumes it's when the velocity is positive, but the velocity being positive does not necessarily mean it's increasing. Okay? It just means the velocity is positive. It could be positive and decreasing. So, concave up between 0 and 2. Very important. This is kind of me walking you through that. If you ask when velocity is increasing, you look at the first derivative and you see when it's positive. That's like when you find if anything's increasing, take the derivative, see when it's positive. But since the derivative is the same as acceleration, just means when acceleration's positive. Acceleration's positive when the position is concave up. Okay? One thing we didn't talk about, which we should have, which we'll talk about now, is speed. Speed is velocity without direction. It's the absolute value of your velocity. If your velocity is negative, the speed would be the positive value. If somebody asks you when is speed increasing, okay? If they ask you when is your velocity increasing, you look at your acceleration when it's positive. But if they ask you when your speed is increasing, it's increasing if your velocity and your acceleration have the same sign. If you have positive velocity and positive acceleration, you are speeding up in the positive direction. If you have negative velocity and negative acceleration, you are speeding up just in the negative direction. Does that make sense? What she said? What she said? Okay. I'll show you that too. You probably saw this with your in your physics class. Okay, so our dude over here. Let's say we give him a positive velocity, and let's give him a negative acceleration. Okay? He goes like this. He goes like that. And hit the wall. Notice, the acceleration is negative, graph's concave down. This is position, this is velocity, this is acceleration. Acceleration tells us the concavity of position. Velocity tells us increasing or decreasing. When we have a 0, that's when we have a maximum, when we go from positive to negative velocity. Okay? When we're moving from left to right, we are slowing down. You can see how the dude is slowing down. You are slowing down when your velocity and acceleration are opposites of each other. Velocity is positive, acceleration is negative. When you are opposite of each other, you're slowing down. Once we cross the 0, we have our maximum position right here, and we start having a negative velocity and a negative acceleration. The signs of velocity and acceleration are the same. You see the dude speeding up, right? And it makes sense that he's speeding up. He's just getting faster in the negative direction. Does this make sense to people? Slowing down, speeding up. Opposite signs, slowing down. Same signs, speeding up. And of course, it does not matter which direction we're going in. Let's say we start here and we have a negative velocity and a positive acceleration. We're slowing down. Now we're speeding up. Signs are opposites of each other. We're slowing down. Signs are the same. We're speeding up. Doesn't matter which direction it is. Notice acceleration is positive. Graph is concave up for position. Concavity here will give us a minimum. Velocity goes from negative to positive. Minimum. Sweet. So speed will be increasing if the signs are the same. Speed will be decreasing if the signs are opposite. Okay. Sweet. Finally, the last unit, especially with approximations, make sure we are careful to consider concavity when we're dealing with approximations. If we have a linear approximation and our function is concave up, we will have under approximations. If we are concave down and we're doing linear approximations, these will be over approximations. If we don't have concavity at all, what are the approximations? Spot on. Exactly. If we have a graph that's linear, well, linear approximations are going to be perfect. Sweet. Finally, the three theorems that we need to understand and be able to apply. Rolle's theorem, mean value theorem, and an intermediate value theorem. Anybody remember Rolle's? Exactly right. Rolle's visually looks like this. We have 2 points that are the same. That means somewhere in between those 2 points, we'll have a slope that's 0. How I state that mathematically, let's say f of A equals f of B. There's some C between A and B where the derivative at C is 0. But this is the picture we need to understand. What about the mean value theorem? Exactly. We connect 2 points. The slope between those 2 points is that. We know that there will be some points between those two where the slope is the same as that slope connecting those two. There. How do I state that? Let's say we just have an A and a B. They could be the same. They might not be. It doesn't matter. We can say that if C is between, or there is some C between A and B, such that the derivative is equal to the slope between those 2 points, f of B minus f of A over B minus A. Intermediate value theorem. We have an f of A and an f of B. There's going to be a C between A and B. Such that f of C will be between f of A and f of B. How do we show this visually? Anybody remember the intermediate value theorem? Say we have that point and that point. What do I know for sure? Yes. That somewhere between the two, if a couple things are true, and we'll talk about those couple things, that we will have to cross the x-axis somewhere. That's the application of the intermediate value theorem. If we connect like that, we will have some C such that f of C is 0, and f of C is between f of A and f of B. Okay? What has to be true for all three of these theorems? Not true. Continuous is for all three. The third one doesn't deal with derivatives at all. We could have a cusp on the third one, and it would still be fine as long as it's continuous. If I went like this, well, we still cross the x-axis here. And this could be any value. It does not necessarily have to be a 0. Okay, all three must be continuous. What about what's so special about these two, Mr. Schrott? Yes. These two also must be differentiable. Okay, that's everything we've learned. Skipping a lot. Skipping a lot of derivative rules and a lot of other rules and stuff. So we know what derivatives are. We know some theorems. We know differentiability, continuity. We know limits. Questions before we start doing some problems?